Hello, I'm Martin Berg. I'm a faculty member in the Mechanical Engineering Department at the UW. And this video pertains to the College of Engineering's Digital Control System Design course, and it will introduce you to the hands-on with hardware component of that course. First, an overview. This component amounts to a series of projects. Each project will require a brief report, and each will involve the design of a discrete time control law and its application, hardware in the loop, to an analog plant. Furthermore, each design will be to meet specific performance, stability robustness, and performance robustness objectives. And if one or more of those terms are new to you, we will be defining them later. So obviously you'll be working with some hardware, and this slide lists three particular hardware components you'll be working with. One is a development system. The second is a National Instruments MyRIO board. And the third is an analog plant. The development system will essentially be your laptop running LabVIEW. And more specifically, it'll need to run LabVIEW under a Windows operating system. And so if you're a Mac user, you'll need to install Windows under a boot camp partition and install LabVIEW within that. Or you can install a Windows virtual machine and install LabVIEW there. More specifically about the LabVIEW software, you'll need to be running the MyRIO software bundle for LabVIEW. And so once you have all that software installed, when you fire up LabVIEW on your laptop, you'll be in the development environment you will use to implement your discrete time control laws, hardware in the loop with the analog plant. So you've been introduced to the development system and the development environment you'll run on that system. And we want to move on next and talk about the National Instruments MyRIO board. If you worked with LabVIEW in the past, you're familiar with its concept of a virtual instrument. Every program in LabVIEW is a virtual instrument, and every virtual instrument in LabVIEW is comprised of a block diagram and a front panel. LabVIEW is a graphical programming language. You program on both the front panel and the block diagram. When you have your program debugged and ready to execute, you go to the front panel, and on the toolbar you click on a Run button. And when you click on that Run button, your program is compiled behind the scenes to create an executable, and that executable is run on your development system. And the resulting output, if any, appears on the front panel of your virtual instrument. For the hands-on with hardware component of this course, you'll need to do something slightly different from that. This need to do something different is a consequence of something purely practical. It's all about timing. In each project, you'll implement a discrete time control law, hardware in the loop with an analog plant, to control in real time the responses of that plant to whatever inputs it's subjected to. The discrete time control law you implement here is one that you will have developed using one of the model-based methods that is discussed in the textbook we'll be using for the course and also in some of the lectures. And behind the development of that control law, there are two critical assumptions. One assumption is that the sampling period is consistent. That is, that the sampling instants happen at a precise interval, and that interval never varies. The second key assumption is that at each sampling instant, the time required to process the current measurement through the A to D converter, to update the control signal, and to route the updated control signal through the D to A converter to affect the analog plant is zero. In practice, neither of those assumptions hold true. If you've worked with LabVIEW in the past, you've probably made use of, at some point, a LabVIEW virtual instrument, or VI, for data acquisition. For example, you may have used a VI to collect voltage data every 1/10 of a second for 5 minutes. Now, in such an application, there certainly is a sampling period involved. It's a 1/10 of a second. But when the focus is on simple data collection, if one of those sampling instants is delayed by a fraction of a sampling period, it's not a big deal. By contrast, when a discrete time control law is used in a feedback control loop, Timing inaccuracies and computation delays can very easily eat up whatever phase margin your closed-loop system relied upon. And when that happens, your closed-loop system will be unstable. And when that happens, the result will often be a disaster. So how can we manage these timing inaccuracies and computation delays? And here I picked the word manage very specifically. 0 timing inaccuracies and 0 computation delays arise only in theory. This, it turns out, is where the MyRIO fits into the picture. First, a bit of background for those of you who have done some programming with LabVIEW in the past, perhaps in some sort of data acquisition application. In so doing, you likely developed a VI on your laptop, which would have been your development system. So you worked with a front panel and a block diagram, you debugged it. If you were out to do data acquisition, you would have to have some sort of a data acquisition device connected to your laptop, probably through a USB cable. That data acquisition device could have been, for example, a National Instruments MyDAC board. In any case, once you had your program debugged, you would go to the front panel and find the run button on the toolbar. When you press that run button, your program, your LabVIEW VI, was compiled. The compiled version of the code was linked with any additional code that the linker would need to find in the libraries that were specified. That would create, in turn, an executable file. And in that standard application, the executable file that was generated would be executed on the development system. Now, in a purely data acquisition application, the execution on your development system of the code that represents your VI might be perfectly adequate. For example, you might have developed a VI that collects data at 1,000 samples per second and displays it on a chart on the front panel. Everything would likely look just fine, but then you might even have noticed that if you, say, held down the space bar on your keyboard, you would see glitches in the appearance on the chart of some of the data. Well, those glitches are a result of timing inaccuracies because your development system has lots of things it's trying to do all at once. And execution of the VI, the code that represents your VI, is going to be a relatively low priority for your development system compared to, for example, keyboard presses, and perhaps even you might have an email application running and you might be getting in email. In a feedback control application, such timing hiccups can't be tolerated. So what can we do? As mentioned earlier, it's not possible to eliminate either the timing inaccuracies or the computation delays, but we can manage them. To that end, one of the things we'll do is to execute the executable code that represents our VI not on the development system, which has too many other things to do, but on a separate piece of hardware that runs its own operating system. And for our purposes, that separate piece of hardware is a National Instruments MyRIO board. But that's not the whole story either, in that the MyRIO doesn't run just any old operating system. It runs something called a real-time operating system, and a real-time operating system is one that's specialized at running processes in real time that require precise timing of events. And just a bit of terminology here, when a process that relies upon precise timing of its events is executed under a real-time operating system such that sufficiently precise timing of those events is achieved, the process is said to have been executed in hard real time. And that essentially is how we'll use the MyRIO, that is to execute in hard real time our discrete time control laws, hardware in the loop with an analog plant. Here finally is a picture of a MyRIO. It's the gray box at the top. As you can see, it's about the size of a couple of decks of cards. It connects to the development system via USB cable. It requires a power supply, and here's the power cord. It has a connector block to which you can wire up all kinds of things. The most important features of it for our purposes are listed here. Number one, it runs a real-time operating system, and we'll use that operating system to implement our discrete time control laws in hard real time. It has several onboard A to D converters that we'll use to generate our measurement signals for our control laws. It has several onboard D to A converters that we'll use to generate our continuous time control signals for our analog plant. And finally, it has a field programmable gate array, which makes for very efficient programming of, for example, our A to D and D to A converters. We've talked about the development system. We've talked about the MyRIO. The last on our list is the analog plant. Shown here is a particular analog plant. We'll be building our analog plants on these little breadboards using standard components, namely capacitors, resistors, and operational amplifiers. The particular operational amplifier chip shown here happens to be a Texas Instrument model. It supplies 4 operational amplifiers. It requires a power supply of plus or minus 15 volts, both of which can be supplied by the MyRIO. Finally, I added this little table to convey some of the reasons why I think this is a good solution for us. Number one, I like that each student will wire up his or her own plant dynamics. Number two, it'll be easy to realize a huge variety of different plant dynamics. Number three, the resulting system is very portable. You could pretty much carry around one of these things in your back pocket. Number four, the cost is low. And finally, number five, no special drivers are required. In just a few minutes, I want to fire up LabVIEW and show you live an application of a discrete time control law to one of these analog plants. But before I do that, I thought I'd show you a circuit diagram of the particular analog plant we'll be dealing with. Here it is. It's a 3-stage system. The middle stage is classic second-order dynamics, natural frequency omega n1, damping ratio zeta 1. The DC gain is 1. Upstream and downstream from that, we have voltage follower circuits, each with a transfer function of 1, but nicely infinite input impedance and 0 output impedance. Let's see here. Other things to note. The particular R and C values I chose give rise to a natural frequency omega n that's very close to 1 hertz and a damping ratio about 9%. So a lightly damped vibration mode at about 1 hertz for this particular analog plant. And finally, thinking about what it would take to, say, add damping to this lightly damped vibration mode with a feedback controller, based on the Nyquist criterion, you can easily calculate that the absolute minimum sampling rate would be roughly 2 samples per second. I have just 2 more slides to show you before I move on to fire up LabVIEW and we do some entirely different things. The point of these 2 slides is simply to illustrate the great variety of different analog plants that one can easily realize using simple combinations of op-amps, resistors, and capacitors. This is the first of the 2, and in it we followed our original analog plant, which has a DC gain of 1, with a simple circuit comprised of a single op-amp and 2 resistors to create a new analog plant that has the dynamics of the original analog plant but a different DC gain. And in this, the second of those 2 slides, we've cascaded with our original analog plant a second vibration mode, the natural frequency of that vibration mode being omega n2 with the damping ratio of zeta 2. And once again, choice of that natural frequency and damping ratio is entirely dictated by the choices of the R's and the C's, in this case, namely R3, R4, C3, and C4. So I've shown you what I wanted to show you with these slides. Next, I'm going to fire up LabVIEW and use it to illustrate an application of a discrete time control law to the first analog plant that I introduced you to just 2 slides ago. I'll be back with that in just a minute. Okay, I'm back. I have Windows fired up on my development system, that is my laptop. I'm about to demo closed-loop control of our analog plant using a MyRio. I'll quickly bring up this picture. So I have connected to my development system. This is obviously just a picture, but I have connected a MyRio. It's connected to my development system with its USB cable. I have the analog plant we discussed a few moments ago wired up on a breadboard. You might recall that analog plant was second order, natural frequency about 1 hertz, damping ratio about 9%. I have wired up this analog plant to the MyRio. Specifically, I have wired the MyRio's analog output channel 0 to the input to the analog plant, and I have wired the output of the analog plant to the MyRio's analog input channel 0, and I have used the MyRio's plus and minus 15 volt pins to power our op-amp chip. So that's my physical setup. I'm going to fire up LabVIEW here, and welcome screen. Here's what I refer to as the getting started window. And what I will do is to create a MyRio project. If you've not worked with projects in LabVIEW before, you'll need to get used to that, because when working with the MyRio, it's pretty much universally the way to go. So under the Create Project heading, I'm going to select to create a MyRio project. It's going to give me a dialog box here. Let's see, I think the first thing I'm going to do is to create a folder where I'm going to put this project, and I'm going to put it on the desktop. And so here's my desktop. I'm going to right click and say new folder, and I'm going to name this folder PID 581, and let's see, and then open that guy, and you can see right now it's empty, and I'm going to say that that current folder is where I want my MyRio project to be stored. It wants me to give a name to my MyRio project. I'm going to use actually the same name, PID 581. All right. Last but not least, I don't see my MyRio showing up. Let's see if I click here. It's looking for a target. It's found one. I have named my MyRio MCB MyRio, and it's showing that name and the IP address. So it's found the MyRio, and I'm going to click on Finish here to create this project, this MyRio project. And so now we're looking at the Project Explorer window in LabVIEW, and it's showing that indeed, here's my MyRio. And under the MyRio heading, we see that there's already a VI there. That VI is called main. And I guess before I go any further, notice that this is the project window for this PID 581 LabVIEW project that I've created. Clearly, it contains more than just icons that represent files. It actually contains an icon that represents my MyRio board. And this is the advantage of building a MyRio project. A bunch of functionalities come built in for you, and it just makes life a lot easier. So one thing I notice, you if you've not seen this before, under to the lower right of my little MyRio icon, I see a green dot, and it's not lit. But if I right-click the MyRio icon and select Connect, it will go out and make a connection to my MyRio, and you'll see now that little green dot is lit up, or maybe you can't see it depending on the resolution of your screen. You might have to take my word for it. So let's explore this VI that by default is created under your MyRio when you create a MyRio project. So I'm going to double click this main VI. Here it is. It turns out that whenever you create a MyRio project, LabVIEW will put in your project a main VI, and this main VI, it's useful. Let me just run it and I'll show you what it does. It's explained here, but when I run it, you see here it's being compiled, and then now it's been downloaded, and now it's executing on the MyRio, not on the development system, but this VI is executing on the MyRio. And it turns out the MyRio has built into it 3 accelerometers, and you'll see, and this is, so this VI, it goes out and grabs the output of those 3 accelerometers and displays it on this front panel window. And not much is happening so far, but when I grab the MyRio and shake it, you'll see that indeed the accelerometers are working. So this is, it's just a nice little check to make sure that your MyRio is functioning properly and you're getting a good connection. So anyway, that can be a good test to make sure everything is squared away before you start doing more complicated things. So next up for us is I want to add to this MyRio project, I want to add a VI that implements PID control of our analog plant. And I have created already that VI and put it on the desktop. So let me see, I'm going to move this LabVIEW project window over here, and I'm going to open up, here's the folder that I created on the desktop that has, this is the root folder for this project. And now this is a Windows, just a regular Windows folder I'm looking at, not a LabVIEW project folder. And so you'll see by creating this project, we put several files in this folder. This PID 581.lvproj, this is in effect the icon that represents the project. And we've got the main VI that I just ran, and I showed you that. But I want to add to this project this VI. It's on my desktop. That's where I stored it. Here it is. And so if I just drag this guy, in fact, I'm going to, I'll just drag this guy to this folder. And now you can see I've added this VI to this folder. The folder name is PID 581 again. The VI that I just added to that folder, the name I gave it was main PID 581. But notice over here in the Project Explorer window, there's no sign of this VI that I just added to the physical folder in which this LabVIEW project has been created. I want to add it to the project, and to do that, it turns out I will right-click on the icon that represents my MyRio and select Add File. And now I want to navigate to that folder, and it looks like by default it took me right to that folder. And here you can see this main PID 581 VI, so I'll click on that. And down on the lower right, I'm going to select Add File. And now you can see that I have added to my project window for this PID 581 project, I have added this main PID 581 VI. So finally we're going to run this VI, and you can see from the Project Explorer window that we're going to run the VI under the MyRio as opposed to running it under the development system, here indicated as My Computer. But here it is. The name is main PID 581. I'll double click on it to open it. And here we see its front panel. And I will bring up the block diagram here shortly, and we can talk about that in some detail. But first, I just want to run it and have you look at the front panel to get a feel for what it's doing. This VI implements PID, closed loop control of the analog plant. It uses, let's see, backwards difference formulas to discretize the what would be the continuous time PID controller behavior. And let's see, the discretization, in connection with this discretization, you choose here on the front panel, you choose the sampling period you want to use, and it's set to go with a sampling period of 5/100ths of a second right now. You might recall that for this particular analog plant, with its vibration mode frequency at roughly 1 Hertz, I indicated earlier that the absolute minimum sampling rate to control that vibration mode was going to be 2 samples a second, and 2 samples a second corresponds to a sampling period of 1/2 of a second, or 0.5 seconds. And so the 0.05 sampling period we've chosen here corresponds to sampling at 10 times the absolute minimum sampling rate to control this analog plant's vibration mode. This box here is where I can enter the time for a run, and have it set to run for 4 seconds. Let's see, in this box we can specify the parameters of a step input. We can specify the size of a step input. It need not be a unity step, for example. We can also specify the time at which the step occurs, and it's set here. The value that's indicated here is 1 second. So in this box, we basically specify that we are going to apply a reference input to this analog plant that is a unit step that turns on at 1 second. Finally, down in this box, this is where we have the opportunity to set the PID gains. And for the first run, I'm going to show you, I'm going to leave all 3 PID gains at 0, just so that you'll get a feel for the open loop behavior of this analog plant when you apply a step input to it. So that's the setup. Maybe I should say that this first window will show us after the 4-second run has completed. We will see on this plot there will be superimposed the reference step input function and the measured output signal. And in the second plot here, the plot below it, we will see the derivative control signal versus time. And for this first run, the derivative control gain is 0, so this is going to turn out to be all 0. But in any case, let me just run this guy to get this step input. And I should mention that you should notice that when I hit the run button, you'll see some activity on a window that'll appear, and that activity is, let's see, it corresponds to this VI being compiled and linked to create an executable file for the MyRio, and then it's going to be downloaded to the MyRio and run there in hard real time. So without further ado, I'll hit the run button. Here's the compile and link activity. Now we're going to run for 4 seconds, and the response will appear. There it is. The white is the step input. You can see that we've got a unit step input that has been applied, or the step occurs at t equals 1 second. The blue curve with the red dots represents the response of our analog plant to that same step input. More specifically, the red dots are the actual sampled values, and I've had LabVIEW plot the blue curve as a staircase function to remind us that we really don't know the analog plant responses except at the sampling instance. So from the blue curve, looking at the overshoot and the period of the waveform, we can immediately see that this response is indeed indicative of a second-order system with a natural frequency very close to 1 Hertz and a damping ratio at 9%. So now that you've seen the open loop response of this analog plant to a step input, I want to add some just derivative feedback just to show you that indeed we can add damping to this lightly damped vibration mode. And I did offline, I did a continuous time root locus for this analog plant. And from that, I concluded that, hey, if we were doing a derivative controller continuous time, a gain of, it turns out, 0.2631 would give rise to a closed loop system having a damping ratio of 90% as opposed to 9%. Now, I'm not implementing a continuous time control law here. I'm going to discretize a continuous time controller with that gain using a backward difference formula and a sampling period of 0.05 seconds. But I should be sampling fast enough that I ought to get performance comparable to what the root locus design predicted. And so let's go ahead and find out. I'm going to enter this root locus predicted gain of 0.2631. Go up here and hit the run button. Wait 4 seconds. And there we have it. Initially, you might be a little surprised that the initial output of our analog plant is at 1. Well, that's because it remained at 1. That was the steady state value at the end of the previous run. So that's why the analog plant output was initially at 1. And so during this first 1 second, the commanded output was 0. And we see this exponential decay to 0. It's not quite reached 0 at 1 second when the reference input switches from 0 to 1. And we see here a second exponential decay, this time to the new steady state value, which will be 1. There is something less than 1% overshoot up here, and that amount of overshoot is entirely consistent with our 90% damping. And indeed, everything we see in this plot is consistent with what we would expect from the, the continuous time design that I did offline, and our choice of a sampling period of 5/100ths of a second. In the second plot, there is shown the the derivative control signal, and the red dots are the sampled values. And so we've got a discrete time derivative control law acting here. It's generating this discrete time sequence indicated by the red dots. That discrete time sequence is being passed to a digital to analog converter, which is doing a zero-order hold between the sampling instance. And so indeed, the blue curve is the derivative control signal, the continuous time derivative control signal that is being put to this analog plant we're dealing with. That's my front panel-based introduction to what this VI can do. Next, we want to look at its block diagram to try to better understand how it does what it does. Here is that block diagram. Now, we could easily spend a half an hour or more talking about all of its details. Instead, I want to rely upon you to download a copy of this VI and poke around in its block diagram yourself to figure those out. I'll just summarize the main points here. On the left, we establish the sampling period in seconds using the front panel control for same. We establish the parameters of the reference step input, that unit step input, remember the step size and the step time. Recall that this VI implements PID control of the analog plant using from the front panel controls for the proportional, integral, and derivative gains. The block diagram nodes representing those front panel controls are here for KP, lower left for KD, and top middle for KI. The gray box in the middle, you might at first mistake it for a while loop. It is not a while loop. The problem with a while loop is it doesn't give us the hard real-time performance, that is, the precise timing that we must have in order to implement this discrete time control law in real time. Now, I'm assuming you've not worked with a timed loop in LabVIEW before, so to provide you with at least a brief introduction, I'm going to right-click on the border of hours, type Control-H to bring up the Context Help menu. Here it is. It's telling us that a time loop executes one or more subdiagrams or frames sequentially with each iteration of the loop at the period you specify. It says to use a time loop when you want to develop VIs with multi-rate timing capabilities, precise timing, feedback on loop execution, timing characteristics that change dynamically, or several levels of execution priority. We will likely not have a need for a timed loop that executes multiple frames, although that is a very powerful feature of a timed loop in real-world applications. We will not have a need for a multi-rate timing. We will most definitely have a need for precise timing. We'll be implementing feedback on loop execution. We will not have a need for timing characteristics that change dynamically, and we likely will not have a need for multiple levels of execution priority, although again, in real-world applications, that is a very important capability. For the hands-on with hardware component of this course, you'll need to be reasonably proficient with timed loops. For that, your only real choice will be to dig in to the detailed help in LabVIEW and to experiment with timed loops on your own. I do want to take a few minutes here to explain how one can set the period for a timed loop. And that's crucial for us because the period of the timed loop is going to be the sampling period for executing our discrete time control law. To set the period of a timed loop, you need to work with its input node. The input node is this little blue box in the upper left. If I highlight it, it shows up in the Context Help window, and we can see that there are several parameters that one can set on the input node. And again, I'm going to leave it up to you to explore this more on your own. But two crucial ones are the name of a timing source. In the particular case we're looking at here, I've specified a 1 megahertz clock as the timing source. The second parameter listed is the period. In the Context Help window, it says it specifies the amount of time that elapses between two subsequent iterations of the timed loop. The unit of the period changes depending on the timing source you select. That is crucial. Here I've selected for the timing source a 1 megahertz clock, so I need to specify the period in microseconds. And if you investigate more closely the code here to the left, that's exactly what's going on. I've taken the sampling period in seconds, multiplied it to create the sampling period in microseconds, and that becomes the input, the DT input or sampling period input to the input node of my timed loop. With that introduction to the timed loop, I want to shift gears here and discuss a bit the code that's inside of our particular timed loop. So I'm going to close the Context Help window. So here's our timed loop. We now know that it executes every dt seconds. This dt being the period of the loop, also the sampling period for implementing our discrete time control law. At each execution of the timed loop, the tasks to be performed are 1. Obtain the current measurement. This is the current measurement of the analog plant's output signal and requires an A to D conversion. 2. Obtain the current value of the reference input signal. 3. Process the current value of the reference input signal through the reference input feedforward control signal path. 4. Generate the current error signal by subtracting the current value of the measurement from the current value of the reference input signal. 5. Process the current error signal through both the proportional and the integral control signal paths. 6. Process the current measurement through the derivative control signal path. 7. Sum together the current values of all of the control signal components. This sum is then the current, also called the updated control signal for the current sampling instant. And 8. Output the updated or current value of the control signal through the digital to analog converter so that it can affect the analog plant. The code you see inside this timed loop completes all 7 of those tasks. I'm going to leave it up to you to poke around in here on your own in order to figure out exactly what happens where. But I do want to make one more point. The analog to digital conversion happens here. The digital to analog conversion happens there. Between the two, we've got the calculation of the control update. And you put all that together and you have a computation delay. The question is, how large is that computation delay? Remember, in theory, it's 0. Well, we can check. And I've added code to our timed loop here to do exactly that. Here in the first frame of this flat sequence, I'm using a tick count VI to grab the tick count in microseconds just prior to the call to begin the analog to digital conversion. And over here in the last frame of this flat sequence, I'm using another tick count VI to grab the count in microseconds after the call to the D to A conversion. Here we subtract the two and we're going to send those to an XY graph on the front panel to view that computation delay at each sampling instant. So having had this discussion now of the block diagram for this VI, I next want to go back to the front panel one more time and look at the results of this calculation of the computation delay. Here is that same front panel view. Recall that we're looking here at the response of our analog plant under derivative control to a unit step input, and the sampling period that was used was 5/100ths of a second. What I did not show you last time was the graph of the computation delay. It turns out that that's just off screen at the bottom, so if I scroll down, you'll see it. Here it is, computation delay in microseconds versus time. The bad news is it's not 0, as theory would have it. The good news in this case is that it is small, at least on average, at about 75 microseconds. It is small compared to our sampling period, which is 5/100ths of a second. So that almost completes the discussion I wanted to have with you about this VI, both what it does and how it does it. I can't resist, before closing, going back to the front panel and running just a couple more cases. And so I'm going to do that. First, I'm going to scroll up to the top. So here we have our same front panel view. Now we're looking here at the results for a sampling period of 5/100ths of a second. Hopefully you recall that we're dealing with an analog plant here that has a lightly damped vibration mode at approximately 1 Hertz, and that in turn dictates an absolute minimum sampling rate for controlling that vibration mode of 2 samples per second. So here we're looking at some results where we've sought to control that vibration mode using a sampling rate that's 10 times that fast, or 20 samples per second. But we've got a really nice opportunity here to explore the use of slower sampling rates. So next, I want to quickly do exactly that. To do it, I'm going to first select the text entry tool, go here to the front panel control where we enter the sampling period, and first I'm going to cut the sampling period in half, so we'll be sampling twice as fast, and I'm going to do that by, I'll put a 2 here between the 0 and the 5. Press the return key, and then I'll press the run button. Wait 4 seconds. So here's what we see, or what we get when we sample twice as fast, arguably slightly better performance. Let's go back now, select the text entry tool again. It looks like we've got it. I'll go back to the sampling period we nominally used, 5/100ths of a second. We'll hit the run button again. Here's the response we saw earlier. Next, I want to experiment with, let's see, cutting the sampling rate in half. So here we're going to go from a sampling period of 5/100ths of a second to 1/10 of a second. So again, using the text entry tool, I'm going to enter 1/10 of a second for the sampling period. Hit the return key, hit the run button. We're compiling, waiting our 4 seconds. And here's what we get. The closed loop performance looks a little bit more shaky, but we're still getting small overshoot and the sort of behavior that we would expect to see under closed loop control with our derivative feedback. Looking at these results though, you might be wondering just how much slower can we go in terms of sampling rate before we start to run into trouble. You hopefully recall from our earlier discussion that for our analog plant here with its vibration mode at 1 Hertz, to control that vibration mode, the absolute minimum sampling rate required was 2 samples per second. You're looking here at closed loop control at 10 samples per second. What if we cut the sampling rate in half again? Well, I don't want to spoil all your fun here, so I'm going to leave that bit of experimenting up to you to do on your own. Thank you for your attention, and have a good day.